variables. So if we have something like this, (5x minus 2y plus 2z), or 5x minus y plus 2z equals 15. (2x minus 3y minus 2z equals 11). (3x plus y plus z equals 4). So this is a system of 3 equations with 3 variables. And I'm going to label the equations A, B, and C again, just so I can refer to them quickly. Now, if you recall, when we were dealing with 2 variables and 2 equations, outside of graphing, I mean, we could graph the equations and see where they're intersected, but the algebraic methods we used involved, the first step was reduce to 1 equation and 1 variable. We either did the substitution or we did that addition or elimination method to get rid of one of the variables, so we had only 1 equation and 1 variable. And of course, when we have 1 equation and 1 variable, we can solve it. Well, when we have 3 variables and 3 equations, now you may have noticed a little bit of a pattern here, a little subtle pattern. However many variables we have to have at least that many equations in order to be able to solve. So if we had 3 variables, we have to have 3 equations or we can't solve it. If we had 6 variables, we'd have to have at least 6 equations in order to be able to solve it. And they have to be unique equations. We saw in the 2 variable systems, we have equations that are the same line or equations that are parallel. Those don't work. We have to have unique equations. Well, our first step here is going to be to reduce the 3 variables and 3 equations to 2 equations with 2 variables. Then reduce that to 1 equation and 1 variable, and then solve. Now, I did these last 2 steps here in a different color because that's just solving a 2 variable system of equations. So we reduce it from a 3 variables and 3 equations to 2 equations of 2 variables, and then we solve that system. So it's all about reduction, getting rid of a variable to make it a simpler system, and then working from there. So today, the method we're going to look at is we're going to look at the substitution method. And in the substitution method, what we do is we solve 1 equation for 1 of the variables. Just like with 2 variables, 2 equations, we find one that's easy to solve for 1 of the variables. And then, that should be step 2, not 3, we substitute into the other equations. And that should give us a system of 2 variables and 2 equations. So up here, I am going to pick equation C, and I'm going to solve for either y or z. It really doesn't matter which one. I'm going to solve for y. Now I'm going to combine some steps here. We're going to do it A little bit rapid because I feel like you guys can handle it at this point. We've done enough of this. I am going to subtract 3x from both sides, and I am also going to subtract the z from both sides. So what I have here on the left side, the 3x is canceled out. I still have the y. The z is canceled out, so all that's left on the left side is y. On the right side, I have 4 minus 3x and minus z. That is my new equation C. Now it's important that I keep track that that is equation C because this has to be substituted back into both of the other equations. So I have to substitute it back into both equations A and B. So equation A, let's do that one. 5x minus, instead of y, I'm going to put in 4 minus 3x minus z plus 2z equals 15. Now I have to reduce this, solve this a little bit, combine what I can combine. I have to be very careful of this minus here in front of the parentheses. Remember, whenever we have subtraction in front of a parentheses, we treat that as -1 times the parentheses. So I'm going to combine on the left side here. I've got the 5x, that's not going to do anything. I'm going to distribute the -1 through the parentheses. -1 times 4 is -4. -1 times -3x is a positive 3x. -1 times z is a positive z. The 2z is outside the parentheses, so it does not get multiplied. That equals 15 so far. And then I still have some combining to do on the left side. 5x and 3x is 8x. Z and 2z is 3z. I have the -4 equals 15. And I am going to add 4. So I have 8x plus 3z equals 19. That's my new equation A after I have substituted my equation C into it. Now let's take a look at equation B. Equation B is 2x minus 3y. But for y, I'm going to enter 4 minus 3x minus z again. Minus 2z equals 11. Now once again, I have some things I can combine here. I'm going to end up multiplying the parentheses. There's nothing to combine in the parentheses, so I'm going to multiply it by the -3. I'm just going to bring down the 2x. There's nothing to do with that. -3 times 4 is a -12. -3 times a -3x is a positive 9x. And -3 times -z is a positive 3z. Now the -2z is not in the parentheses, so it is not multiplied. And now I can combine. 2x and 9x is 11x. 3z and -2z is just 1z, or just z. I still have the -12 equals 11. And now I have to add 12 to both sides. Get 11x plus z equals 23. That's my equation B after I substituted in my other equation. So what I have now is a system of equations in 2 variables and 2 equations. I have my new equation A, which is 8x plus 3z equals 19. And my new equation B, which is 11x plus z equals 23. Now at this point, this is a 2-variable system. I could use substitution again, or I could go to the addition or elimination method. Doesn't really matter which one I use. I'm going to go with substitution again just because equation B is sitting there staring at me with that z really easy to solve for. I'm just going to subtract 11x from both sides. And I get that z equals 23 minus 11x. That's my equation B. I'm going to substitute that back into equation A. So 8x plus 3z, well, z is going to become 23 minus 11x equals 19. Now I have some simplifying, combining to do. All right, the parentheses, there's nothing to do inside the parentheses. So I'm going to multiply by the 3. So I'm going to bring down the 8x, nothing to do with that. 3 times 23 is a positive 69. 3 times negative 11x is a negative 33x. Equals 19 yet. I can still combine here. 8x and negative 33x is a negative 25x. Plus 69 equals 19. And now I can solve for x. We'll subtract 69. Negative 25x equals 19 minus 69 is a negative 50. And I divide by a negative 25 to get x by itself. X equals 2. So I have found x. All that work, and I only have one variable found so far. We still have to find the other two. Now, fortunately, one of the advantages of this substitution method is it makes it really easy to find the other two. We go back up here. We have this equation b here that is solved for z. So now that I know x, I can put that in here, the 2 in for that x, and I can get z rather quickly. So z equals 23 minus 11 times x. Well, x is 2. Well, 11 times 2 is 22. 23 minus 22 is 1. Z equals 1. Now from there, I can go back up to my equation C here that I solved at the very beginning. Y equals 4 minus 3x minus z. And I can substitute z equals 1 and x equals 2 in there. Find y. So y equals 4 minus 3x will be 3 times 2. Minus z is just going to be minus 1. Order of operations. 3 times 2 is 6. We're going to go left to right. 4 minus 6 is a negative 2. And negative 2 minus 1 is a negative 3. So the solution to this system of equations is x is 2, when y is negative 3, and z equals 1. So you might be looking at this wondering, why didn't we just graph them and see where they intersect? Well, that is a great question. If I wanted to graph with 3 variables, with x, y, and z, our graph, there's our x-axis right there. The y-axis is like that. Now that's a right angle, even though it looks like it's angled. It's perpendicular. It's just an orthographic view. Z comes straight up like that. Just plotting a single point on this coordinate system, because I'm trying to represent 3 dimensions in 2 dimensions on a flat surface, just plotting a single point gets very cluttered. Let's plot the point y equals 2, x equals 5, and z equals negative 3. So for x, I go 1, 2, there's my x equals 2. Y equals 1, 2, 3, 4, 5. That's y equals 5. And z equals negative 3. 1, 2, 3. That's z equals negative 3. To find the single point where they intersect, well, the only way I can make sure I get to that point is I use rectangles. And I find, actually, what I'm making here is a box. So I connect, make that rectangle there between x and z. Should have done this one first probably, the rectangle between x and y. And then I make the rectangle between y and z. Now that forms, if I consider the axes here to be the other edges, 3 sides of a box. If I go out here, if I extend this over and down, and this up, this here, that is that point. That 8th corner of my box is the point. X equals 2, y equals 5, z equals -3. So just graphing a single point on a 3-dimensional graph is really a pain and very cluttered. Without this wire-framed box there, I wouldn't have any clue where that point was and what it represented. So now try imagine graphing a line on here and making it obvious where that line goes. It just isn't feasible. We can't do it. And trying to see where lines intersect, same thing. It's hard enough to find out where they intersect in 2 dimensions. With 3 dimensions, we just can't do it. So graphing is not an option. The algebraic methods here are the only way to go for solving systems of equations once we get to 3 variables. This actually, by the way, turned out pretty well for me trying to draw a graphing in 3 dimensions. I can actually see where that point is if I stare at that long enough. Helps if I get the yellow out of there maybe. I can actually see how that point is sitting down there. But it's a strain, and I've seen these graphs enough to be able to pick it out. I imagine many of you are looking at that graph probably doesn't make any sense to you, and that's fine. We're not going to do any graphing in 3 dimensions. So let's get back to a 3-dimensional system of equations. Let's create a system here. So we're going to have 3x plus 2y plus z equals 8. 2x plus 3y minus 3z -1. 5x plus 2y plus 2z is 8. So now if we want to graph or want to solve this, I'm going to label these equations A, B, and C. Remember our first step, step 1, pick one equation to solve for one variable. And here there's an obvious one for that. Equation A solved for z. It's the only variable in this whole system that doesn't have a coefficient on it, which means we don't have to divide by anything when we solve for it. So that'll be an easy one to solve for. So equation A, we're going to solve for z. So I've got 3x plus 2y plus z equals 8. Now, once again, I'm going to take some kind of a shortcut here. I'm going to do 2 steps at once. I'm solving for z, so I'm going to subtract 3x from both sides. That would cancel out the 3x. I'm also going to subtract 2y from both sides. That'll cancel out the 2y. So what I'm left with here is z equals 8 minus 3x minus 2y. That's my new equation A after I solve for z. So that's equation A is the one I've solved. That means I have to go back and put that into each of the other 2. If I put it back into equation A, it ends up canceling everything out. We end up just with a 0 equals 0, basically, is how it ends up. So let's go into equation B here. Equation B, I'm going to put it over here. 2x plus 3y minus 3z. Instead of z, I'm going to put an 8 minus 3x minus 2y equals negative 1. So I have some combining I can do here. I'm going to multiply. There's nothing I can combine inside the parentheses, so I'm going to multiply by the negative 3. So my 2x and 3y are just going to come down. Nothing to do with those quite yet. Negative 3 times 8 is a negative 24. Negative 3 times negative 3x is a positive 9x. And negative 3 times negative 2y is a positive 6y. Equals 1. Well, we are still combining here. And combine 2x and 9x is 11x. 3y and 6y is 9y. I still have the minus 24 equals 1. And the last thing I need to do to solve that is I'm going to add 24 to both sides. I'm not really solving it, but I'm getting it in that form, x's, y's equals constants that we're used to. So the 11x and the 9y are still there. The negative 24 cancels out. On the other side, 1 plus 24 is 25. So that is my revised equation B after I substitute it in for z. I still need to do equation C. I'm going to pause for a second for you to catch up with your notes for a minute. I see some of you writing furiously, so I'll wait a minute. So we still need to go back to equation C and put that expression in for z, equation A. So in equation C, I have 5x plus 2y plus 2z. Well, for z, we're going to put in 8 minus 3x minus 2y. That equals 8. Now, in the parentheses here, there's nothing that we can combine, so we're going to multiply by the 2. So our 5x and our 2y are just going to stay the same. We have 2 times 8 is a positive 16. 2 times negative 3x is a negative 6x. And 2 times negative 2y is a negative 4y equals 8. We have more that we can combine here. 5x and negative 6x is a negative 1x, or just a negative x. 2y and negative 4y is a negative 2y. And of course, we still have the positive 16 equals 8. Now I'm going to subtract 16 from both sides to get it into that form again, x's, y's equals constants. So I have the negative 1x, or negative x, if I want to just leave it that way. Let's just do that, negative x. Minus 2y. I subtracted the 16, so that's gone. 8 minus 16 is negative 8. This whole equation here is negative right now. So what I'm going to do is this. I'm going to multiply the whole equation by negative 1 to make it positive. That doesn't change anything. As long as I multiply every digit of the equation. So negative 1 times x is positive x. Sorry, negative 1 times negative x is a positive x. Negative 1 times negative 2y is a positive 2y. Equals negative 1 times negative 8 is a positive 8. So that is my new equation C. So the new system that I have that I need to solve here consists of equation B, which is 11x plus 9y equals 25. And equation C, which is x plus 2y equals 8. Well, I can solve equation C for x. I'm just going to subtract 2y. X equals 8 minus 2y. That's my new equation C. I have to put that back into equation B. So 11x becomes 11 times 8 minus 2y plus 9y equals 25. So again, I got parentheses here, nothing I can combine inside, so I'm going to multiply by the 8, or sorry, by the 11. 11 times 8 is 88. 11 times negative 2y is a negative 22y. The positive 9y is outside the parentheses, so it does not get multiplied. So I combine negative 22y and positive 9y is a negative 13y. 25. This is technically my equation B. I can now solve that for y because it's in a single variable. So let's do that. I'm going to subtract 88 from both sides. Minus 13y equals, what is that? A negative 63? I feel like something went wrong here. Oh, let's see where it takes us. What's the worst that can happen? I don't see any blaring mistakes, so we'll keep going with it. Okay, so we're going to divide here to solve for y by negative 13. So y equals, negative divided by negative is a positive, 63 over 13. Well, 13 goes into 63. Four times, which would be 52 with 11 left over. So that's a 4 and 11/13. That's y. Now we can go back and find our other variables. This was equation B. Our next step here, equation C, is already solved for x in terms of y, so we can find x there. X equals 8 minus 2 times y, of course, is 4 and 11/13. Well, 4 and 11/13 times 2 is 9 and 9/13. We subtract 8 minus 9 and 9/13 is a negative 1 and 9/13. Now we still have to solve for z. We go back up to our original that we solve for here. Z equals 8 minus 3x minus 2y. And I put in 8 minus 3x is going to be 3 times negative 1 and 9/13. Minus 2y will be, y will be 4 and 11/13. So I've got 8 here. A negative 3 times a negative is going to become a positive. What is that? 3, 5 and 2, or 5 and 1/13, actually. And let's see here. Minus 9 and 9/13. There. So we have some combining to do. We have 8 plus 5 and 1/13 is 13 and 1/13. Minus 9 and 9/13 is 3 and 5/13. So our solution as ugly as it is, it's a solution. X is -1 and 9/13 when y is 4 and 11/13 and z is 3 and 5/13. So the moral of the story here, the big key here is when I got to this point where I saw that y equals 63 divided by 13 and that does not divide out evenly, I did not just do 63 divided by 13. Because that decimal, even what the calculator is giving me, is rounded. That actually repeats every 6 digits for this one. It's 4.846153, 8461153, 8461153. It's rounded off. If I tried to use that decimal to find x and z are going to be rounded off because of that. So we need to start, as uncomfortable as we might be with them, as much as we don't want to work with them, we need to start working with the fractions. So when you get something like 63 divided by 13, if it doesn't divide out evenly, treat it as just an improper fraction and reduce it down to that mixed number. These are a lot of work. As you can see, in 35 minutes, I got through 2 examples. I would put one more example up there, but I really don't think we have time to do a full example. So I'm going to do a simple example here. So let's do this. 2x plus 3y minus 4z (13). (3x plus 5y is 34). And 2y equals 10. So I'm going to label these equations A, B, and C again. What we notice here is they don't all have all of the variables. The first one, equation A, has x, y, and z, but the other ones are missing 1 or 2 of the variables in them. This type of system of equations is tailor-made to be solved with substitution. Even if, in the next couple of days, we will look at the addition or elimination method. Actually, Wednesday, because tomorrow we'll go over more examples of substitution. But even if we knew that method and had that method ready to go, this is a system we would want to solve with substitution. Because equation C is already only one variable. I can solve that for y by simply dividing by 2. Y equals 5. I already have one of my variables. Then I can go to equation B with that. 3x plus 5y, well, that's 3x plus 5 times 5 equals 34. Well, 5 times 5 is 25. I can solve this for x. I only have the x variable in it. So I'll subtract 25. 3x equals 9. And I'll divide by 3. Get x equals 3. So I have y equals 5, x equals 3. I can now go back to that first equation and find z. 2x is 2 times 3, plus 3y is 3 times 5, minus 4z equals 13. Combine what I combine. 2 times 3 is 6. 3 times 5 is 15. Now I know Technically, I just did 2 steps in the order of operations at once. I multiplied working left to right, and I multiplied both of them in the same step. Because they're separated by an addition, I can do that. It won't affect my result. If it was 2 times 3 times 5, I'd have to be careful. Then I'd have to go step by step. Now here then, I can combine 6 plus 5 is 21. So 21 minus 4z equals 13. And now I'm ready to solve that. I will subtract 21 from both sides. Negative 4z equals 13 minus 21 is a negative 8. And I'll divide by a negative 4. You get that z equals negative 8 divided by negative 4 is a positive 2. So that gives me the solution is x is 3 when y is 5, and z is 2. So there's a system where even though it's 3 variables, we actually buzzed through that in about 5 minutes because not every equation had all 3 variables in it, which made it a lot easier to solve. So in Blackboard for today, it's of course week 14 folder, November 30th, is a worksheet on 3 variable systems of equations. On that worksheet, I want you to do the even numbered problems. We'll go over those problems in class tomorrow. Make sure that you guys have it down as to how to solve them, and then we'll go on from there. So we have about 9 minutes left here. If you'd like to start, if you have access to that worksheet and would like to start on it, I'll be on the network here to answer questions. Otherwise, since I can see you're all working from home today, if you would like, you are free to go.